Perfect. Good morning and welcome everyone. My name is Elisa Junqueira de Andrade. I'll be your moderator today. And this event is part of a series of seminars that is organized by NTNU Energy and our team Nuclear, where our goal is simple but very important: help create informed, balanced conversations about nuclear power. And over the past months, we've seen the headlines. It's sometimes a heated debate around nuclear energy, some misunderstandings happening around us. So it is a topic that brings up a lot of strong opinions, but where many people feel that they don't have enough knowledge to participate in the debate. And today is about building that foundation in a clear, accessible, and neutral way. To guide us through the fundamentals, we are lucky to have Professor Thomas Allen Adams II with us. He's a professor at the Department of Energy and Process Engineering at NTNU, leader of our team Nuclear at NTNU Energy. His research spans sustainable energy conversion systems, advanced power plants, hydrogen, biofuels, and of course, nuclear energy, with a focus on modeling, optimization, system-level thinking. Today, he has the challenge of teaching us nuclear power in 40 minutes. From the physics to fission, how reactors work, and how nuclear can fit in the modern energy system. Tom, floor is yours. Welcome.
Thank you very much. Okay, welcome everybody. It's great to see you. Okay, so yes, we're going to try to talk about nuclear energy in 40 minutes. So I'm going to take a lot of shortcuts. We're going to keep things simple as much as I can, because we're targeting sort of a public audience. So this is being streamed on YouTube. These are being recorded so that we can have a library of information for people to learn from the general public. So we already, thanks for the introduction. So in terms of mentioning NTNU Team Nuclear, we're one of 14 teams at Team Energy, so at NTNU. So in our particular case, it's a group of professors, researchers, and students, and we're all interested in nuclear energy in some fashion. So for our particular team, we have research that's very interdisciplinary because we come from all across campus. So for example, in power systems like myself, and systems integration, materials, medicine, but we have also people interested in ethics and the regulations and philosophy and things like that. So we're scientists, engineers, and even philosophers looking at this in a sort of interdisciplinary way across the spectrum. We are politically diverse, and by that I mean people are very pro-nuclear, very anti-nuclear, and then all across the spectrum in between on this team. Okay, so as a team, we are politically neutral. So our goal for NTNU Team Nuclear is really about developing and expanding knowledge and the research of it. And so as a team, we don't take a position. We also run, we have different energy courses, or nuclear energy courses. We have a nuclear energy course that's for, master's and bachelor's level that's extremely popular. We have some PhD level courses and things like that. But primarily we want to create an educational base for our university, but the country as well. So our common goal is really about building up the expertise within Norway. So these workshops are really more about the general public and expanding that information outside. So we have this big debate right now: will nuclear power be developed in Norway? And so this workshop is really just about the basic information to get started. So our workshop series, we have this through this year and then more coming next year from different people around the country in terms of industry or academia and other experts on different aspects of nuclear energy within their own expertise. We're doing this one in English. The other ones will be across the country in Norwegian, and then we'll have mixes as we go forward, depending on different speakers and things. So you can check our website, ntnu.edu/energynuclear, to get more information. Okay, so that's the background. And I also want to put everything into context. So today we're going to have kind of two halves of like 20 minutes each. The first will be a science part, and then we can take some questions, then we'll have a little break, and then we'll have an engineering part. So I think that's a good way of looking at everything as quickly as we can. But the context of why we're here, I think we need to start with that. Okay, so everything that we need to be concerned about as engineers and scientists, if we're inventing ideas, if we're developing processes, in order for that to be successful, it has to be sustainable in all three aspects of the triple bottom line of sustainability. Okay, we have to be economically sustainable. There has to be a business case or it's not going to happen. And that's lots of things like cost, profits, it's things like uncertainty and financing. There's all sorts of elements that go into the economic side. And now we have this environmental side. Over the last 20 years, that's increasingly important. Not only are we concerned about things like greenhouse gases, but we need to be concerned about all these other aspects of the environment. I work with water as well, quite a bit, as well as the greenhouse gases, but things like particulates and acid rain and smog. There's all these other factors. We don't want to maybe save one and be terrible in all the others, for example. But the third one, and this is especially important, probably more than any other kind of power technology for nuclear, is the societal sustainability. So if you can have something that's totally great business case, great for the environment, let's say, but if the public does not accept it, it's not going to happen. And I think nuclear falls into that category. And this is going to be depending on that particular region or province or country, right? Wherever you are. So you have NIMBYs. Does anyone know what NIMBYs are? No? What are they? Not in my backyards. Perfect. So NIMBYs are everywhere in all things that are constructed and built. That's always a factor. What are bananas? Anyone know that? Absolutely correct. Build absolutely nothing anywhere near anyone, and those are also a big factor as well, increasingly so with nuclear power. And there's many other things. So it's perception, it's emotion, it's feelings, it's electoral politics. There's so many factors. And so in order for it to actually happen, all of these have to go. So, and that's the basic context of where we are in the country. This is one of my favorite diagrams to explain how different aspects of energy relate to each other. In energy systems, we sometimes use a metric called energy return on energy invested. Okay, and it's basically a metric. It's a ratio of how much energy you get in a product divided by the amount of energy it took to make that product. Okay, so it's a nice ratio to kind of return on investment. The biggest thing I can find here is up at 900. This is the Bagger 293 coal miner. Over here, this is basically a giant behemoth machine that just rips the earth apart to get at the coal. All right? It is basically a stuff of nightmares, but is an engineering marvel at the same time. All right? This 900 means approximately, as I can calculate, for every 1 ton of coal's worth of energy that you spend to run this thing, we can rip out enough to get 900 tons of coal out. Okay, that's what it means. And the bigger, the more efficient. That's where we have gone now. Okay, the biggest I can find for hydroelectric is about 200 in Canada and province of Quebec. That means for every kilowatt hour of energy I spent to build and run the dams and everything, I can get 200 kilowatt hours of electricity back. That's why it's such a powerful and low cost and low environmental impact energy source, which we have throughout our country here in Norway. Oil in the 1930s, so 100 years ago it was 100. So for every barrel of oil I spent to drill and pump oil, you could get 100 out of the ground. Okay, that was back then when it was low-hanging fruit, it was easy to get. All right, modern coal mining is about 80, so this is with traditional mining that's modernized. Oil in the 1970s is about 30 because we've taken the low-hanging fruit. We're getting offshore now, we're getting farther down. Okay, wind is very good at 18. So you build that wind turbine and you leave it for years, you can get 18 back times. Modern oil is about 15. Okay, so we've gone from 100 to 15. That shows you how oil has been an order of magnitude more difficult to get. We're very far offshore, deep down in the ocean floor, for example. Modern natural gas power is about 10, and nuclear power is about 10. So when it comes to actually making electricity, these are on some of the highest end of things that we deal with at scale. Okay, so that's where we put at in terms of nuclear power. Solar panels, 7 to 9. This number means you have to run the solar panel for 3 to 4 years before you get the energy back it took to make that solar panel with all the mining and the fabrication and everything. But then after that, you get your energy return. Okay, but you have to go for 3 to 4 years. Sugarcane ethanol in Brazil is the best biofuels in the world at just above 5. Canadian oil is about 4 to 5, so this is where I'm from. That's where most of our economy is based on 4. And then all the way down to corn ethanol in North America. 1.2 is a very generous number. I've seen a lot of numbers go below 1, which is entirely unsustainable. Okay, but this is where we are in perspective. Okay, and then the last factor is why we talk about it so much is where it falls in the environmental side with regards to CO2 emissions. So what I have here is a chart of different kinds of power plants. At the very top, we have modern coal power. Okay, they're building one a week of these in China and India. All right, and this is the sort of the carbon footprint, so it's the grams of CO2 equivalent per kilowatt hour of electricity, and that's up there at 944-ish. Okay, these are just round, fuzzy numbers here. And then as I go down, we see the average footprints of different countries. So Mongolia, for example, is almost all coal, so that's why it's a very high number. As we go down, South Africa, again, mostly coal, India, China. And as the numbers go down, it's because they're using less and less coal. All right, so we get down to the world average at about 470-ish, which is about what a natural gas power plant would be. So natural gas is a little bit less than half of coal per kilowatt hour in terms of carbon footprint. US and Germany. Okay, now these blue ones are different sort of carbon capture systems using coal. Okay, in the 200s, the UK, Canada, very advanced chemical looping power plants. We don't really have those yet. Advanced natural gas with carbon capture, 115. Okay, we've passed solar with batteries already. Okay, now we're down here to the most advanced kind of fuel cell power plants with 100% capture. This is the lowest I think a fossil fuel can ever get. It's 50 to 70. There's France and there's Norway, under 30. Okay, Norway is one of the lowest in the world in terms of carbon footprint. You can see it's just orders of magnitude below the very top. And it's because of hydro at the bottom, okay, because hydro is one of the least carbon intensive ways of power, and nuclear is right there with it. So these are very fuzzy. I don't think you can even know that order, actually. All right, but I've given hydro the benefit of the doubt and put it at the bottom. All right, and so what that means is for Norway, if you are going to build more and you don't want more CO2 to raise your footprint, you can only choose from below your number on this list. Okay, there's not much choice here, right? And there's only so much you can expand for hydro. Hence why nuclear is in the discussion. So now I think you understand why we care, right, for this country. Okay, so I'm going to talk about the science. I'll try to simplify it as much as I can because we're going to do it in about 15 minutes. We'll take some questions at the end of the first segment. So hopefully you remember the periodic table of elements. It's not something, I'm a chemical engineer, so we deal with this a lot. But in the basic premise of nuclear energy, we care about uranium. We're just going to talk about that. There's other things, but we're going to really talk about uranium. I'm going to point, if you remember the little number in the corner, the atomic number, that's the number of protons it has. Okay, so for example, hydrogen has just one, and helium is 2. The number of protons defines the letter in the name. So if it had less protons, it would not be uranium, it would be other things, okay, if it goes down or more, right? All right, so we care about this. That number is the average atomic mass. So if you add up the weight of all the protons, the neutrons, and the electrons, which are a rounding error, that is the average found on the Earth, which is about 238, because basically almost all the uranium found on the Earth has 143 neutrons in it. That makes it uranium-238. All right, now, we'll talk about why that matters a little bit later, but in general, a nuclear reaction is simply taking that atom and you break it apart into usually 2 pieces that are smaller. Okay, so in this example, if you have a uranium you're splitting, in this example you might have a barium and a krypton. Okay, so 56 plus 36, that adds up to 92. Okay, so it's just the same number of protons, but they split. How it splits can be very different. It can just go all sorts of different ways. All right, so that's the basic premise, and when you split it, it releases energy we capture as heat, and we use that heat to do work. That's a power plant. An engine, engineers, the name comes from building machines that take heat and you turn it into work. Okay, work is, you make that into electricity. Okay, so that's the basic premise. We're gonna take things that are big and make them into smaller chunks. Okay, so the process of that is called fission. All right, we're going to focus on uranium-235. Okay, so I had 238 here. We want that 0.1%. The 0.1% that we care about is 235. That's the stuff we can actually use and exploit for nuclear power. Okay, so it has 143 neutrons to go with it. Okay, and basically, the primary way we're going to do this is through neutron capture. So the idea is that you have a neutron flying around, and it will basically be absorbed into this nucleus of the 235, and within a split second, it splits apart, okay, with some probability distribution. And basically, you're going to get your 2 other atomic cores. Okay, they're gonna split apart, but this is the part we like. 1, we get a bunch of energy we're going to use as heat. 2, we get more neutrons, so more pieces fly out, and that's useful. And then we're going to also get gamma radiation, okay? Now that's the dangerous part, but we can also capture that and get some heat from that as well, all right? So the whole premise here is that these parts are useful, the heat and these things, okay? So basically the reason why this is special, without getting into too much details, in order for this to happen, there's an energy barrier you have to overcome. So whatever gets sucked in there has to be enough energy. But 235 is special because it's one of the very few isotopes or versions of uranium or other atoms where just getting one neutron is enough, okay? And because of that, we use the word fissile to describe that material. Okay, so it's just a very convenient, very useful, right? Just kind of, most things are not useful for this purpose, all right? The first law of thermodynamics around mass balances basically is going to tell you that the mass before and the mass after the reaction has to be the same. So what we can think about is the number of protons I have before, which is 92, and the number of neutrons here, and the total is 144, has to be the same when I add it all up on the end. Okay, so they're just moving around, basically. Okay, so it's a simple law, and that's how we hear about it here. And the other factor is that we have more neutrons than released. These can vary, 2 to 3, but more neutrons than what we put in. That lets us do a chain reaction. That's very, very useful as well. Okay, so we'll talk about that. Okay, so those are the key properties that we want. Now, the first law of thermodynamics also says, just like mass before and mass after have to be the same, energy before and energy after have to be the same. So a similar way to look at it is the total energy, if I add them all up before, has to basically be the same as after. Okay, so over here, it's not to scale, it's just a cartoon, but before I had less kinetic energy, and my energy was mostly internal. Kinetic is like how fast it's moving and how hot it is. That's basically kinetic energy. Internal has a lot of stuff, but there's potential energy stored in the bonds of, in the interactions between the different atomic particles, like the proton and the neutron, for example, okay? There's potential, it's a fuel. Okay, because what I can do is if I can convert that internal energy into kinetic energy, so my new products have a much higher kinetic energy, they're moving fast, and they're hot. Okay, it's the heat I care about. That difference is the heat I produce, and I care about it, and it's a lot. I also have some energy going to that gamma radiation, which is small, but we actually can recover that as well as, and use that as well as heat. Okay, and in fact, this is so big that this is what makes nuclear power special. Now, one problem here is that these particles that we get, and there's a whole spectrum of them, they usually keep decaying on their own, and they can have other reactions with neutrons as well and things like that. Okay, so this basically becomes what we call radioactive waste. Okay, so this is the material that's what's left over that you've probably heard of. Okay, that keeps going. Okay, and I talked about how much energy. That's a lot. Let me show you just how much this is, why we like it so much. Okay, now this is a table of fuel. You know what wood is. You probably know coal. You probably know diesel. And then over here I have the energy content, the thermal energy content. Okay, this is the amount of energy I get by combusting it, by burning it. All right, so these are rough numbers again, but for wood it's roughly 16 megajoules per kilogram of wood. Okay, for example, diesel's about 40, it's a very good fuel. Natural gas, hydrogen's very, very potent. It's rocket fuel, actually. All right, 142. Exergy, basically without going to detail, using the second law of thermodynamics, this is the maximum amount of electricity you could ever produce with the perfect system. So it gives you a sort of a chance at the amount of electricity you could make with the fuel. Okay, and it's gonna be very similar to the heat. All right, now uranium is there. Okay, so you're looking at millions, tens of millions per kilogram of stuff. Okay, this is a phenomenal difference. Pure uranium, 235, 78 million megajoules per kilogram. Okay, if I used it. But it's so potent, we don't do this. Weapons grade uranium is even lower. All right, but what we use is enriched uranium in power. Okay, so that means it's like maybe 2%. So in this 2%, means it's 2% uranium-235 and the 98% the other uranium that's everywhere. Okay, the 238, that's not the potent stuff. Okay, but it's still 1.5 million kilojoules per kilogram of electricity potential. What that means is if I had a gigawatt power plant, which is like a big power plant, okay, it's enough to power 1 million homes, I only need 400 kilograms a year of this mixture, 2%. All right, that's nothing. Compare that to coal, which is 1.2 million metric tons a year. All right, so this is the energy density and the potency that we care about a lot. So that means very small amounts, you can do a very large amount with it. Now, I mentioned that gamma radiation. This is a big part of the science stuff. Okay, radiation. I don't need to go into all those details, but essentially, all of these different types of radiations can happen in a nuclear reaction. Okay, and there's lots of things going on there. I talked about those other isotopes, and there's other things happening. Okay, there's really three kinds. Alpha is really just 2 protons and 2 neutrons together. It's just a helium atom. Helium's inert, generally, without its electrons. This kind of radiation can't even go through a piece of paper, so it's just, we don't even really care. It's not going to hurt us in any way. All right, beta emissions are things like electrons, and again, I'm oversimplifying everything. That can go through paper, but it can be stopped by your hand. And gamma radiations are things like X-rays, so they can actually go through your body, but they're stopped by concrete and things like that. Okay, and the frequency of this radiation varies depending on the different kinds of reactions and things happening. My very first part of my career was actually in radio frequency safety around things like cell phones and microwaves and things like that. So depending on the frequency and the dosage and the different parts of your body, some of these can be dangerous depending on it. Okay, depending on the amount. So in my first job, it was about protecting workers near microwave emitters and things like that. Okay, and we know the science behind it. Okay, so this is why in a nuclear reactor it's shielded by concrete, because it doesn't go through the concrete. Okay, so it keeps it inside. Okay, so let me talk about that chain reaction again. This is the same diagram we had before. So you have that 1 neutron, and it might release 2 or 3 or more or less, but let's say 2 to 3. Now, once that's released, those 3 neutrons can then go on to interact with 3 more uraniums, right, quite quickly. And then that might release, now we have 9 neutrons flying around. Those can go on to interact with more. Maybe we're at 27 neutrons flying around. Okay, and then now we have more and more and more and more and more. And if there's heat being released as we go, you can see this exponential growth, right? That's a chain reaction. This is kind of the extreme end of it. Okay, but it's a cartoon. Okay, that assumes every neutron immediately hits the uranium, which immediately splits and does all these things. Okay, and if you can achieve this, you get this. Right, so a weapon would be doing this at very high volume and very, very quickly. That's not what we want. So it's useful, I'll explain in many, many ways. If it's uncontrolled, there's problems, okay? You can have runaways and things like that. But it's actually hard to achieve this because there's so many other factors, both by nature and by design, that kind of prevents this from happening, that works against us. Okay, there's anti-factors here that counterbalance. So the science of it is, if we're going to try to harness this potential, we need to balance those factors. Now, one thing that happens is we have a flying neutron. If it is going to interact with the nucleus of our uranium, okay, you can see this is very tiny and this is very, very tiny. So how do you have a very tiny, fast-moving thing hit a very tiny target, right? That can be difficult. So if it goes too fast, it can fly right by. It can hit it and bounce off if it's the wrong angle or the wrong energy, wrong speed, okay? But the useful part is, actually, we don't have to hit this target exactly. If we want it to interact, if it goes slow enough, it'll actually be sort of captured. It goes to it. Okay, so there's all these different sort of energies and angles and things that, right? It'll still go in, but you don't have to hit the target. The target is actually much bigger, okay, than this tiny little thing. I'm losing audio in and out. Yeah, don't know what's going on there. Okay, so a lot of the design is to try to get these neutrons to have, so that they kind of hit the targets with the, they'll actually go in. Okay. All right, yeah, where's it going to go? So neutron capture is the idea that it's going to be sucked in and interact there. Okay, so the whole engineering now, which is part 2, is about how do you build the systems to make all these happen in the right way. Okay, I think that's the end of part 1 for the science part. I think we can take some questions now. I think we'll have some coffee and then we'll resume for part 2. So are there any questions or anything?
Yes, the mic's working, so questions?
I can't resist asking. When I teach thermodynamics to my students, I say that kinetic energy on a micro level, internal energy on a micro level is kinetic and potential energy. But in your slide you had kinetic energy and internal, that one.
Yeah.
So what is kinetic energy here? That is different from what I tell my students, that it's atoms and molecules that have kinetic and potential energy.
There's all sorts of different forms of kinetic energy in terms of translational, which is movement, rotational, spins, things like that. The main thing I want as far as the science aspect of it for learning it in 40 minutes is the heat part. So temperature is another word for the average kinetic energy. Okay, so they're the same thing. And the point is, I'm going to get more of it. I didn't fully hear everything actually with the audio coming in and out with all the full question. I'm trying to kind of categorize them very simply. I don't know, maybe you need to repeat the question if what you were telling your students, because I didn't hear that with the audio.
Can I try this one instead?
Yeah.
Is this one working?
I think so, yeah.
Okay, so energy is, for our systems, is like internal energy, and then kinetic energy, and potential energy on a macro level, right?
Well, potential energy in my case would be included in internal.
I know.
Okay, all
so
right.
what I tell my students is that the internal energy, I mean, there are two kind of mysterious terms in thermodynamics. Internal energy is one, and entropy is the other one. So I tell them that internal energy is also kinetic and potential energy, but at the micro level. So it's the atoms and the molecules. So it's the electron orbits, it's the bonds between the atoms. So when you say here kinetic and internal, for me, since you are on the micro level, I don't get it.
All right, this is what I would like the takeaway to be. Internal energy is essentially the potential of any fuel that you have to be converted into some other form, I would say. That's a really good way to think about it. So if this was a fuel, okay, like a normal fuel like wood or gasoline or natural gas, the internal energy would include the chemical potential of between the atoms. So that would be like the carbon-carbon bonds, the carbon-hydrogen bonds. So we call that internal energy. And then when you combust it, it's released as kinetic energy, which would be temperature, okay? I want that same thinking here in a very, very crude, basic science way, where the potentials that are inside of that atom is the potential to be converted through splitting, and the energy that's stored basically in the atomic interactions between the parts can be converted out. I have a star here, right there, which I didn't mention, and I took out the little part of it, is that actually we have mass and energy linked together. So what I'm being overly simple about, because of E equals mc squared, right? So you actually can have the mass of this be converted to energy. So like the number of particles is the same, but they get a little lighter, and that can be converted to energy. I've skipped all that. Okay, so I think your question has so many deep levels that I think I'll end it there. We can talk more after.
Next question.
I would like to go back to the slide where you show the capital costs, or the costs per energy.
Oh, the energy return.
Where you compare the different.
Is it this one?
No, perhaps the other one. This one.
The
yes.
greenhouse gas emissions.
Sorry, it's the CO2.
Yes.
Some of this. When you come down to the different technologies, are, I would say, you have a mix of mature and not so mature technologies.
Yes.
I assume that these numbers are, say, as of now, the current status of these technologies as of now. But what would you say can be the potential of some of these when these are mature and established technologies, optimized? technology?
Yes. Okay, that is a fantastic question. And it's a fantastic question because I've done 10 years of research into figuring out those numbers. So the basic question is, where are we at in terms of maturity? So again, I said these are fuzzy. Each one of these numbers are the result of studies where we looked at literally hundreds of different published studies about each of these plants and where they could go in the future. In this case, every single blue one is basically the best I think they will go. Okay, so these are things which are not fully mature and they're not fully developed. Okay, the modern coal CCS this happens in Canada. We have these plants. There's some new ones going around the world. Okay, these other ones, for example, IDCC, 2 of these were built in the US, but they were both shut down and switched to natural gas because they were so terribly expensive to run that it was better just to not even do it after spending $10 billion to build them. Okay, these have never been fully commercialized at scale. This is the best I think it will ever go, is 50. I don't think we can go much more than that. Maybe a little lower. This is in America. I think if we put this at a wellhead in Norway where they both produce the gas and capture the CO2 at the same spot, we might get this down to 45. Okay, so this is sort of like the future we're heading. Now, the green ones, okay, I think this can come down. I don't have wind because honestly the wind literature is so much over the place I couldn't put a peg. I put wind like there. Okay, so that's not helpful, so I just don't have it. And nuclear, this is argued about, hydro's argued about, so these are very fuzzy. I hope that answered the question well enough, yeah.
Questions? Yes, one more, and I guess then we move to the second part.
It's a bit more of a general question concerning the thermodynamics. If you could go to the slide where you showed the exergy of the different fuels.
Yes.
This slide. I don't understand. How is it that some fuels have more thermal energy than their exergy and some fuels have less thermal energy than their exergy?
Some of this, okay, for some of them, it's because there's other factors like there's that pressure. Some of them it's because they're basically different units and they're compared against different things. That's a really good question. Another really good answer is they came from 2 different sources. And I think that's really your true answer. So with one of the things, this is so very interesting. So Truls and I have a book on exergy, specifically in terms of calculating these numbers. So that's where I get these from our book.
I don't know why I'm running a diesel car.
Yeah. So these are really, really fuzzy because there's blends of things like that. Basically, the general principle is exergy can never be higher than the total energy supply of that thing, the total energy content. But this is heat released from combustion only. And these measurements, actually, this is a higher heating value very specifically. A higher heating value does not include the latent heat, the specific heat between 25 Celsius and 150 degrees Celsius, because this is literally an 1800s unit to explore and trade on. Okay, so there's actually more thermal energy content available in these combustible fuels than there is in the exergy. Okay, now, so these are actually from our book, and these are actually the correct numbers, because if you include that additional energy that's not there in these tables, you can eke out a little bit more work in a very perfect environment, which we can't actually achieve. Yeah. Great.
Now it's the final question.
Thank you. Oh, thank you for an excellent presentation. Social scientists here, and we understood quite a lot of what you were saying,
Good.
so it was great. But I wondered if you could go back to the table that shows the triple level,
Yeah.
the three columns.
Oh, 3 columns. Sorry.
Yeah.
You mean the greenhouse one?
No. The one with the society.
Oh,
yeah, the
this
right-
one. Oh,
yes.
sure. Okay.
Yes. You have on the societal, you have public acceptance at the top.
Right at the top.
And I was thinking for the future.
Yeah.
Would you consider taking that out?
Taking out? I'm sorry?
Public acceptance, yes.
Taking that out
Yes.
as something important.
Yeah, it's something quite important to think differently about how we work with society. So not thinking that they are accepting the technology, but rather thinking about how can we work alongside society, maybe offer local communities some dignity in the processes. So it's just a different way of thinking about how we move forward. So, I mean, it's very common in engineering contexts that you talk about public acceptance, but it's one of the challenges in the energy sector. Yeah. So I'm putting this out there. I'm not saying you have the answer. I'm just sort of putting this into the room to sort of, something to think about.
Okay. I mean, to be honest, I didn't fully understand, because you're proposing that public acceptance should not be at the table. That was what I heard.
Yeah, I would think you should put maybe public dignity or something else. It's not about acceptance.
Public dignity.
Yeah.
I mean, that could go in. I mean, engineer, so I do numbers and stuff. So when it comes to the feelings and emotions, I'm going to not claim any expertise.
I think one of the things that, to agree with what Ruth, it suggests a one-way flow, right? That engineers are developing things so the public can actually accept, and might go back and forth. So it's the name or the way it's presented that is the thing. Does that make sense?
That makes a lot more sense.
Yeah.
Right. I'm thinking if you got a whole bunch of protests and everyone's just going to walk away from the project, then you're done. That's basically what I'm thinking of.
Yeah, I think we agree. It's just that the term that's used is the, yeah.
Okay. Thank you.
Okay, so I guess we're moving to the second.
Yeah, maybe if you want to grab some coffee.
Exactly.
And we'll take it
you
back.
and we fix your mic before.
Yeah, okay, great. Take a
Perfect.
quick-
Okay, for those online, we'll be back in 2 minutes tops. I think the sound issue was fixed and we've got our coffee, so we can come back to the second part of this presentation.
Okay, test, yep. All right, I think we're back now. Great. Okay, so I'm going to talk a little bit about the engineering side of it now. And I think for time I'm going to have to shorten it a little bit. But the whole point of engineering is to apply the science. That's what an engineer is, an applied scientist. So how do we take all these theoretical principles and we put them to use? Okay, so first I want to give an overview of the sort of life cycle. So one of the things that I work with is life cycle assessment, and we want to look at basically the cradle to grave process, or in this case, in our words, product system, for how nuclear energy would be put to practice to make electricity. So we have this yellow boundary here. We call that the environment, and so things come in and go across that boundary when we're taking things out of the earth or putting them back in, maybe through emissions. Okay, so what we start with here is uranium ore. So if we find uranium ore that a certain percentage of it, maybe 1%, maybe 0.5%, has the 235 component of it that we want, the rest being primarily 238. Okay, and that's rocks, that kind of thing, we mine it. Okay, that takes energy, and there's some greenhouse gas emissions associated, so think of like diesel and drilling and whatever's involved. Okay, and we have to get it somehow and convert it to a form that we can use in our power plant. Okay, and without getting into too much detail, I think we're going to skip the fuel production part, but we need to do what's called enrichment in most cases. All right, I'm being overly broad here, but enrichment is basically the process where you take out some of the 238 so that the percentage of 235 remaining is more. Okay, and you might want to get to 2% or 3% or 4%. There's a whole process for doing that. You might have heard of the word centrifuge. Okay, so centrifuge is a device that just spins really fast, and it basically creates essentially kind of an artificial gravity, like in the centrifugal direction. So it means the heavier stuff gets pulled toward the outside, all right, and the lighter stuff gets pulled toward the inside. And basically 235 is 3 neutrons lighter, so it's a little bit more going to be likely to be on the inside than the outside, essentially is how we do it, okay? Breaking it down very simple. So what you need to do is that takes energy, and it takes time, and basically you're trying to densify and get a higher percentage. We don't need to go to 80, 90%. We're going to like 2, 3, 4, 5 for most things that we're going to care about for this talk. Okay, and that takes some energy. All right, and so when we talked about that energy return on energy investment of 10, that's where you put it in. Essentially, is what we're talking about here. Okay, so then we're going to build special fuel packets because we're going to shape it, we might treat it, coat it, there's some other things in there, right? So we're going to make a really nice product, and that 400 kilograms of that per year we're going to send to our nuclear reactor. It's like one truck. Okay, so that we load in, and then this is going to be running continuously. And the general premise is we have a good stable reaction. Okay, it produces heat. We want the heat to go to our electricity generation system, and then we're left over when we're done with our sort of spent rods. So remember, we break down all that useful uranium. Well, we don't break it all down actually, but we break down enough. And then we have our other broken parts, the other materials in there, that becomes the waste, and that has to be stored. We don't throw this back into the environment. We don't dump it in a river, right? So we keep it from going across that yellow boundary. So that's what nuclear storage, radioactive waste storage is. Once we have that heat, we need to get it to our power plant. So we use a coolant. A coolant is a thing that goes into the reactor, and it gets hotter or takes thermal energy in other ways, like, for example, boiling water to make steam, and then that is carried over to our power system, and that's the engine. Okay, so and then we once the heat goes off, this is cooled again, and we send it back. So this is just a loop, okay, and this is overly simplified because you could have loops and loops and upon loops and things like that, but the general premise is I take heat away and put it in my power plant. We're going to use a steam cycle or some kind of power cycle to produce mechanical power by spinning a turbine, and that's attached to a generator, and that produces our power for the grid. Okay, and this part is very much like any thermal power plant. So if I combust gas or combust coal, especially in the traditional sense, this is kind of the same. It's the same principles. The details are different, but once I have the heat, it doesn't really matter if it came from a reactor or combusting coal or natural gas or something. Now, the problem is if I trace the energy, so the energy supply started here, okay? We're losing little bits as we go, or spending it as we go, okay? I'm going to transfer the energy, we're changing form. Once I get to here, only 1/3 of that heat will actually be converted to electric power. So it means the plant is about 33% efficient. Again, overly generalizing, but it's not 50 and not 10, okay? The other 2/3 of energy, it just goes somewhere. You have to put it somewhere, so we send that to the environment in the form of evaporative cooling towers or other kinds of cooling. So when you see the sort of classic cooling tower shape, it's actually just the cooling system. That's not the nuclear reactor system. Okay, but this is what people see and they're connected to emotionally and internally. Okay, but we only get about 1/3, but 1/3 is enough because that energy density, as we saw, was so big that it's worth it. Okay, so now if I want to design a reactor, all right, again, there's many, many different kinds. The general principle is that you need to achieve a balance. Okay, so we have that chain reaction. If we don't have the chain reaction, then we don't produce enough neutrons and we fizzle out. All right, but too much, and we can go the other direction, and then it's getting too hot, and you got a problem, right? You need to control that. Okay, so the whole point of all the systems are devices and tools and techniques to balance them and keep them balanced. All right, so some things that make more neutrons or fissions, you want to have the same number of fissions per second, so the heat rate is the same. You can do things you have to do things to start it up, so you have to spend energy in special ways. I don't want to go into those details, but you need to like get it going. Okay, that's it. You got to start it up. Okay, that takes energy, but you hopefully don't need to do that very many times. You just do it once and let it go for a year, let's say. Okay, you will add things like potentially a neutron reflector. It's like a mirror. Basically, if your neutron misses, you don't want it to just go flying out, hit the concrete, or go, get leaked out, right? You want it to bounce back and go back in again, so it has another shot at hitting a different uranium, right, that you want. So you're going to put things in there. You want to keep these neutrons are very valuable. You don't want to lose them, right? They're hard to produce. So you got to really work to keep that. We also have something called a moderator. There's fluid. I'm familiar primarily with deuterium. This is heavy water. So the Canadian design uses this. So this is what I'm most familiar with. But you need things where basically materials where the neutrons don't get captured or caught up, they just slow down to the right speeds. Because if they're too fast, they'll kind of fly it by in many cases, right? On the balance of probabilities. All right, so you need these materials to kind of regulate it. We want them to go slow without getting caught. All right, but on the other hand, there's things that we can do to reduce the number of fissions so it doesn't go too high. One thing is you can just have simple non-fissile materials, things that will absorb a neutron without causing for like actual nuclear reactions. So like just the parts in there, if they hit it and it won't cause a reaction, then you'll lose that neutron to that thing. So that counterbalances it. And in fact, we use that in something called a control rod. Okay, so these are materials that literally they can absorb the neutron without causing further reactions. And basically, if you need to reduce the neutrons, you push them down more. Okay, and then there's just more to absorb. And if you don't have enough, you can pull them out. So that's the main control thing. There's like computers that are constantly monitoring and they're going up and down all the time, every second. You want to maintain the right amount, so that gives us precise control. Very useful. Okay, so we do that in a sort of a negative feedback. The more negative feedback we can put in, the less reaction we have. One thing we do by design is, again, we have dilute fuels. We're not using pure uranium. We're using this dilution. And so you have other things in there that are not going to be producing a net surplus of neutrons by design. Okay, you can have a poison. So scram is the term for like emergency. So you have a button called scram and you hit it and it would dump boric acid. There's a whole bunch of things that would dump into the reactor and they just absorb the neutrons, so then they prevent them from reacting with further uranium. So it's an emergency shutdown apparatus. Okay, and things like that. Okay, and I already mentioned the thing about the things. So the whole point of a reactor is to carefully balance all of these factors so that you have steady state. So in chemical engineering in my world, steady state is the rate is constant. It's not going up and down all the time. And you can design them where you can do that, but for the most part, right now we're gonna think about steady state only. Okay, and we wanna do that while getting heat constantly and producing electric power constantly. That's the point. Okay, so the engineering tries to maintain that. Okay, there's many different kinds of reactors. This is a simple example, I think, to explain how it works. Okay, this would be a large containment core. These are things like steam generators. You can see some offices over here for scale in this particular example. And this little red one here, this is like a reactor unit inside this big zone, okay? And this is a very simple cartoon. Okay, coming into this, we have our coolant. So this is gonna come back from like our cooling system, the cooling towers, right? So this is the cold stuff we put in. You know, it could be quite warm actually, but we call this the cold side. Okay, and it's gonna flow in here, it's a fluid. Okay, there's different ones you can use, water, you can use deuterium, you can use helium, there's all sorts of things you can try. All right, and when it goes in, all right, we have our fuel section, that's the yellow, so that's where the nuclear reactions are taking place. Those are fuel rods, and that's where the reaction's happening. That's producing the heat. We have a moderator. Okay, so those are the things that will not capture the neutrons, but slow them down to the right speeds to maximize the chance of them being kind of reflected back and keep reacting. We have our control rods, so these are gonna go up and down. So the more it's in, the less reaction we have, and we can pull it out, so they're just going up and down all the time. All right, and then what the point is, the heat that's released will go into our fluid. Okay, it could just be water in this case. and then it comes out hot. Usually this is pressurized water or steam, and we're going to have high temperature here. Okay? So that is the basic part of a reactor. So this is just going, and these are going up and down to try to keep this as constant as possible. All right, this, I don't need to go over the design, but this would be like a real design of one. Okay, you can see there's lots of little rods here that are going to go up and down. You can see like inlet for the coolant and come out one of these other sides, for example. It's going to flow around in there. We got the little holes that the rods can go up and down. We got fuel sections. That's what it really looks like. Okay, we don't need to worry about that today. But you can see the point. All right, lots of extra safety layers and things like that. Once we get that heat, this is the entire field of engineering in one slide. Okay, so converting heat to power, I really didn't know how to do this in one slide, but we're going to give it a go. Okay, the basic premise is that for at least a steam cycle, you boil water, you push that water over turbines to produce electricity, and then you have to send the water back as a liquid. So you have to condense it, and then you send it in the cycle, okay? So we're going to start here, okay? And we're just going to use a boiling water reactor concept where it's just trying to be as simple as possible. That's your coolant in. It's going to go at high pressure, and we want to heat it up to make it water vapor, so steam at high pressure. All right? This is a diagram that shows you the state of water without, I don't want to get into too many details. This is pressure. This is enthalpy, which you can think about how much thermal energy it is. There's multiple things in here. That dot is atmospheric temperature and pressure. That's 1 bar and 25 Celsius. All right? The hotter it is, it goes to the right. This is the phase line. So this is a liquid. So it's liquid water, room temperature, pressure. If I add more heat, it gets hotter and hotter. That's 100 Celsius. Then it starts to boil. I get the first bubbles of vapor. Boils more, boils more, boils more. When I get all the way out here, now it's all steam. And then if I keep heating it, it gets hotter and hotter. All these black lines are more and more temperature. Okay, it just gets hotter and hotter and hotter. All right, we're going to start up here. In this case, I've drawn it at 60 Celsius and and much higher pressure. What is that? 10, 20, 30, 40, 45 or so bar atmospheres. Okay, and so what I'm going to do is I'm going to heat it up. There's a whole system here, but I'm going to ultimately use the heat from that reactor to basically get it to 0.2, and that's what's going to come out of the reactor now. That's the coolant exit. So I want to have a high pressure, high temperature steam. Okay, and this can actually be a little bit more to the right. It's a cartoon because it's so variant. Okay, but there we go. I'm going to come out high pressure, high temperature, and I'm going to send this to a turbine. And that's going to produce my shaft work. All right, these red lines they're something called entropy lines. Basically, the best turbines you can ever make will follow a red line. Okay, so the most efficient, it follows that red line perfectly. Okay, so if I have a turbine, what I can do is I can reduce its pressure while producing work and following approximately the red line. Okay, so I'm going to go down a little bit. The width there between 2A and 2, that energy is the amount of work I produce in the turbine. Okay, so I want to go as far to the left as I can if it's a good turbine. Okay, it doesn't go very far. I'm going to add some more heat and move it here. And then I'm going to send it through another stage of turbine and go down again, so I produce more work in that width. It's quite a lot. Okay, and that sum is what I actually produce. And now I have a bunch of waste. It's just, I can't use it anymore. It's weak, low pressure, wet, not very warm, right? So I just need to get it back up to number 1 and send it back to that reactor again. So the rest of my process is to use condensers. That's our big cooling tower. And then I'm going to use a pump and send it back up, okay? So a steam cycle is just going around this diagram, taking heat in, producing power, and then moving it back again. So cooling it down so I can get it back into my pump and put it back up again. That's basic engineering, hundreds of years old. All right, and that's how it works. These are attached to generators and you get power. This is an example of a real system in Canada for how we do it there. Okay, yes. Okay, and this is the first stage of turbine. These are the second stages. All of these red boxes are ways of moving heat around. There's our generator that produces electricity, like you have the copper coils spinning, electric fields, that kind of stuff. There's our condenser that's connected to our cooling towers. We got some pumps. Okay, so it's the same thing, but just more complicated with lots of spaghetti of pipes. Right, everywhere. All right, so this is an example for what it looks like. One turbine, you'd have 2 of these plus a high stage one, high pressure one in this. Very, very big. This is actually inside of a casing. This is a rare look on the inside, but it's a very complicated thing that spins and turns this giant shaft. Okay, and that's basically where we end up. So what I've hopefully showed you now is how we can go through and take the energy from the uranium out of the ground, refine it, enrich it, transport it, use it to convert it to heat, convert that heat to power, and convert the, shaft work, and that's convert to electric power for electricity. And we get 1/3 of it, the other 2/3 lost to the environment, which is actually pretty normal for how these things work. Final slide. Again, we talk about steady. Right? I picked a week in Ontario last year where they have a large amount of nuclear power. This is what I'm familiar with. This is a week last year in a very high demand, difficult week to produce electricity. What you're looking at is during a very hot part of the year. This is the total power produced in the province. Okay, green is what's produced by wind. The yellow is solar. You can see it's not very much. Nuclear is this big, steady, doesn't change, constant for a week, the whole week. Right? I think I can see a pixel, maybe, change, right? Hydro they use to go up and down in Niagara Falls, okay? Produces a large amount of water, but they need natural gas to cover everything else that they don't have. Okay, this is a very high demand week. Sometimes this is often zero. In Norway, we do almost all of this with just hydro, the baseline and the peaking, up and down. So if we were to do this in Norway, it would probably look a lot like this, except that gas is all hydro. We would just have the hydro doing this part, but we can lift the base up and do a lot of the work with nuclear so that we can increase our power production but still maintain these peaks, like that. Okay, that's the end of engineering. Hopefully you're all ready to go design power plants and build them. All right.
Thank you, Tom. We could maybe have 1 or 2 questions before we move to the panel. I don't know if anyone has a question ready to go right now. Yes, we have questions.
Okay, so now you talked a lot about the traditional way to produce energy from nuclear fission, which is this steam cycle which has been used for many, many, many years, right? So I wonder whether there's been some research going on into some more sophisticated ways to harness the nuclear energy than just kind of the primitive way of transferring it to heat.
Yeah, so that's a really good question. So you can take my nuclear course. With many of the instructors are here, actually. So the technology I've shown you, so the CANDO this system is from the 60s, 70s, 80s. You know, the reality is that we have been the technologies have been advancing on paper for a very long time. We use something called generations. Okay, so generations, the first generation was like the 1950s. This one is, which one? What we call generation 2 plus, or 2. In this case, it's a classic just heat and steam cycle. Generation 3, those are being built now, and those do exist mostly, or what's running. 3 plus is being built now, I'm sorry. Those are basically more advanced versions of this where they're still, from almost all of them, we have a steam cycle with just more efficient ways of doing things. So higher temperatures, you know, higher pressure. So it's just basically doing that, moving the points of that diagram out more, okay, on that pH diagram, pressure enthalpy diagram. But then we have generation 4. Generation 4 are things like molten salt coolants. We're not using water. Helium coolants, that's actually where I've done my research on. Because you can get to very high temperatures, for example, with a helium coolant, 800 Celsius or more. Okay, and then at that point, you don't even have a steam cycle. You go through gas turbines directly, so you don't even have the steam in the loop. Actually, you do. You take waste heat to make steam, but your first cycle is actually running gas through a turbine directly. And then you have fusion as well, so that's a completely different world, which I actually don't know a lot about nuclear fusion, but that's all the theoretical side of things right now. I hope that answers the question without going too much into detail. Yeah, but I think on paper, there's so many great ideas. It's a matter of getting them out there. Yeah.
Next question.
Yeah, hi Tom. My question is related to this one and the previous one. Because on the previous slide, the pressure enthalpy diagram, there was no superheating. So
yeah.
I was, when I saw this, I thought, oh, this is just illustration purpose.
Yeah.
So, I mean, the steam turbines don't really like to have water. So when you move to the next flow sheet,
Yeah.
I thought this is what is actually going to be. But I read 64 bar, 281 Celsius. That steam is really not superheated because I looked in the steam tables yesterday, and 64 bar is at 281.9.
It's about there. That's 270. Yeah, so it's going to be about up here. Okay, so a couple things. One, it's a cartoon, but so superheating, what he means by superheating is that that point should be farther away from that line. Okay, so this is an example of that point is superheated. That's what he's talking about.
Yeah.
Okay, so he's criticizing my cartoon. Thank you, Truls. Okay.
But it says the same on the flow sheet if you go to the next one. It says 64 bar to 81 Celsius. The saturation temperature at 64 bar is 280.9, so it's just 0.1 degree away.
Yeah, okay.
That's not really superheated.
It is, okay. It's enough that you should not have droplets. But in nuclear power, okay, so now we're going to get in the details of that 33% efficiency, and we're going to get the details of like what could we do to improve, right? And this is actually where these are improving. In most power plants, and what he's talking about, is that these lines, they come into the phase diagram, phase envelope here. Okay, that point lands inside that. In a coal or natural gas power plant, they don't. We actually take it way far outside and take it down until they hit, go out again and take it down until they hit. The reason for that is because to build this thing moving at 10,000 RPM and to handle water droplets slamming against the side is very technically challenging and very expensive, okay? Those power plants can operate 500 Celsius, 550 Celsius. We are safe in generation 2 and 3 technology at 260, 280, okay, way lower. Because of that, we actually spend the money to build ultra-resilient turbines that can handle up to 10% moisture content, liquid moisture, okay? So the reality, Truls, is that in fact we go 10% of the way inside, okay, up to. And there's an economic trade-off for how much you can handle. There's all these optimization factors there. And it's because we're absolutely eking out every single bit of efficiency we can and spending capital at the expense of perhaps, because it's more efficient, or it's actually less efficient to not go inside, all right, for a given temperature. So we're going to actually voluntarily spend extra capital to eke out just a tiny bit of efficiency because we're going to do everything we can with what is frankly a very low temperature reactor. Generation 4, we want 800, 500. 3+, we're increasing this, okay? So that's where we're headed because that means we don't have to do what he's saying. Yeah.
Okay. Final question, because I think we had a lot of questions for Tom, and thank you very much, Tom. That was very helpful. And I will invite you to take a seat, because we will now bring 2 more people to answer questions so that it's not all on you today. So I would like to invite Rolf Jonas Persson, who is an associate professor in the Department of Physics at NTNU. So you said you didn't know much about fusion. I guess we have someone who can answer those questions for us right now. His work spans atomic and nuclear physics, physics education, and the history of physics, so very helpful. And we are also counting on Professor Emeritus Truls Gundersen from the Department of Energy and Process Engineering at NTNU as well, contributing widely in thermodynamics, process integration, and energy efficiency in industry. And we will open the floor for questions, but if I can start, we saw a little bit of those gigantic towers, Tom, and you mentioned like that they use mostly for cooling, etc. And we had a meeting before where you said that there's already some alternatives that don't look as intimidating as those gigantic things. So, and also there's a lot of talk about also small modular reactors. I'm not sure if these two connect, the non-towers and the small modular reactors. So I would like you to first explain what those are. And also, I was wondering are these hyped, overhyped, or are the small modular reactors a feasible potential technology that could be implemented and would make sense for us?
Okay.
So maybe you start explaining what these are, and then we can take the panel to comment on whether this makes sense and the height.
So you've touched on some really interesting points. So in terms of the cooling tower, so we're used to the giant hourglass shape. Basically, in engineering generally, and this is to the small modular point, in general, go big or go home because of economies of scale. So the progression of industry is essentially dealing with economies of scale. The larger economies of scale you have, the less expensive it is per unit product. And these are manufacturing and widgets. It's true for power in most cases. So when we build these nuclear power plants, the capital is so intensive because you want to eke out that sort of return in the long run that they might build them at 4 gigawatt, 8 gigawatt stations, right? So these are very, very big. And so one of the things in terms of that cooling tower, there is an emotional attachment to seeing it. Like I remember the first time I saw one in Pennsylvania, I was driving through the turnpike and I go around a mountain, I'm like, right, you just go and there's this giant cooling tower and you're like, oh, it's a nuclear power plant, and everyone's a little uncomfortable in the car, right? So like that is absolutely a factor. In France, they have some cooling towers that are much, much shorter. They're just kind of a circle, and you may not even see it because they're about the height of the tree line. Okay, so what they do though is you spend some of your electricity to pump fans and get things moving. Okay, because the cooling tower is just basically a giant chimney, and you have this natural convection that can kind of suck air in and cool your system. That's why they're so big, because the bigger the chimney, the more airflow you get and the more you can do with it. But if you spend electricity, so you're going to have less efficiency, you don't have to build them. So there's some cost benefit, there's some visual benefits as well. And that brings us to the second question, which is about small modular. So small modular is really just a small nuclear power plant. The theory is you build them at much smaller scales. They could be, instead of 1 gigawatt, they could be like 10 megawatt maybe 1 megawatt. Okay, and the point is if they can be small and self-contained, there's potential user benefits. Like there may be just so difficult to build many gigawatts, like I just only need 10 megawatts or 1 megawatt. You might find more customers, more people can use it. But the smallness of it, when you talk about the height, okay, it's related to those economies of scale, because a small thing should be or more expensive per unit kilowatt hour, like it should be. Okay, but the sort of the idea that's put forward is, okay, well, I'm not going to make money on the size, or I'm not going to get economies of scale on the size. I'm going to get economies of scale on mass production, because if I can standardize the part, right, and standardization of parts, like that's Henry Ford and industrialization generally for the revolution. Standardization of parts, mass production. You can control things like regulation. You keep things small. You make it simple to operate. Then you're saving costs per number, right, and per usability and all the side factors that go in with permitting and delays and everything. That if I can just deliver a product, I can save a lot of money. So it's a completely different strategy to try to achieve that same thing. Is it a hype? The answer is I don't know. I would say all the literature on like whether it's better to have base load or small modular, I think they're completely 50-50 in terms of the theoretical literature. I really don't know. There's a real case for like there's just more users and there's just a bigger market for it. That might be enough. Whether or not it's more expensive or not might not even be relevant.
Okay, and maybe Rolf and Truls, do you have an opinion?
One comment, or a few comments. In literature, I think the definition of SMR is it's up to like 300 megawatt, but they are producing larger. So in Ringhals in Sweden, they have ordered 3 Rolls-Royce SMRs, and each of them is, if I'm correct, 470 megawatt. So that's I also read yesterday from our colleague in NTNU Ålesund, Jan Emblemsvåg. He put out a story on Facebook about from the International Atomic Energy Agency, and it refers to the NOU report from Kjernekraftutvalget, who sort of said that it's going to take 20 years to build something like that in Norway, and the International Atomic Energy Agency, they suggest that a country can go to build an SMR. It's going to happen in 10 to 12 years, which is about half of what Kjernekraftutvalget suggested. And that is for a country that doesn't have any background in nuclear power, which is not the case for Norway. We have an atomic energy law. We have, I don't know how to translate to English, it's Direktoratet for Strålevern og Atomsikkerhet. We have experience from research reactors in Halden and Kjeller, and we have IFE with a lot of expertise. So we are not starting from scratch. So it's going to, for me, reading this is going to take less than 10 years to build something in Norway. And that has been an important argument because we are facing greenhouse gas emissions and we need to do something with the heating of the world. And according to Kjernekraftutvalget, nuclear power is not going to be the solution to that because it's too far into the future. I doubt it is that far into the future if we want to go for it now. So those are my comments right now. Yeah, and SMR is what we are actually talking about in Norway, right? We're not talking about building conventional plants. Yeah.
Well, the problem with SMRs, as Tom rightly said, if you scale it down, you run into trouble because they will become more expensive. But the other side is you need to have highly enriched uranium. Instead of a conventional nuclear power plant where you have 4 to 5% if it's cooled with ordinary water, you need up to 15–20%. And the Norwegian laws do not apply to this degree of enrichment. So you have to create the whole new juridical system to handle these. The second thing is that the SMRs that were ordered, they don't exist right now. They're vaporware. That's another issue because as far as I know, there are 4, medium-sized SMRs running now, 2 Russian and 2 Chinese. Yeah. The Russian ones are having serious trouble. They have a duty cycle that's less than 50%. The Chinese I haven't seen. And taking the history into account, and that's also one of the reasons that nuclear power plants in Europe and during this time has become so expensive, is that you need to test them properly. You don't have a ready-made product. You have to do adjustments all the time. So once you produce an SMR, you need to produce another one, and these would be the test reactors. And then you learn how to run these reactors, and then you can see, can these be used directly, or do you need to do some modifications again? And with each, you add several years. So 10 years, yeah, wishful thinking, I would say, but 15 to 20 years, then it's more feasible. But that comes in taking everything into account. The physics is there. The physics says this will work. So it's an engineering task and an operational task. And that's where most of the delays will be, in addition to the juridical issues that come up. And then also public acceptance of SMRs.
Thank you very much. Audience, they already have questions. That's so bad because I have a big list of things I wanted to ask, but I have to share, I guess. So we're starting off with questions over here.
Yeah, thank you. That's really interesting that it might be possible to have 10 or 12 years rather than 20 or 30 years. So if that's the case, if we can imagine nuclear energy that could be developed over a shorter period of time, what do you think about the other things that could be put in place to make sure that it's not something that's kind of parachuted in, right? Do we need education programs to ensure that local people can work in these, to make it more, if we use the word social acceptance, so we can avoid the controversies and problems that other forms of energy have had in terms of, does that make sense? So I'm talking really widely, and I want to know what you think. Education, how will it work with local communities? They need to see a relationship to this new energy form in Norway. So I just wonder, anything you can say about what needs to happen around the engineering stuff and more in like the people things?
So that's a really good question. You can jump in. I'm just going to start. So as my role in NTNU Team Nuclear is largely like the big picture is education generally, and it's the research is also a form of education as well. Educate our PhD students and learn new things for ourselves. Right now, if you haven't followed the sort of the government Charne Energy Utvalg report, I'm sorry, my Norwegian is terrible, but basically the government report committee that came back on nuclear energy, and the primary conclusion was we need a national competency building project in this country because we need competency for the engineers, for the physicists, for the operators, for the general public. We need people to do like the regulations, we need the lawyers, right? We need, and then all the paranuclear stuff like emergency preparedness and disaster response, security because of all the proliferation risk, like all of those issues. So one thing that we're developing, I don't have a perfect answer because we're actually giving an official NTNU response. We're in development of exactly what we need to do to educate the public. You know, this workshop series is one of the very first simple things we're doing to get the public out there, just access to more information. The report that they gave was hundreds of pages, but it is a fantastic Norwegian language resource that gives you information generally about nuclear, and I recommend that any Norwegian read that because I don't think we had an excellent Norwegian language big primer for the public before, really, at least in recent times, and it's very up to date. So basically my answer is we're developing those skills right now, but it has to be research, it has to be education, and then it has to be all of the para sides, and then the public needs to know, right? And my number one thing that I've done as the leader of Team Nuclear, which hasn't been very long, it's just people calling me, they're like, what is it? Like, how does it work? Do you have any information, right? So we started from almost nothing, right, in terms of what nuclear education is in this country, so we're trying to develop that.
Mm. Yeah, that's correct, because radiation in general and nuclear, there are words that are, well, they have a very negative sounding. People are afraid of radiation with, well, actually with no reason at all, because that's the only thing we know a lot about what the damage will be, and we know how to protect ourselves. But it's invisible. And that makes it difficult to have a discussion like that because people get very scared. If we look at the risks, make a risk analysis and look at what kind of damage will we get from radiation compared to pollution. Pollution, we don't know the effects at all for most compounds, but with radiation, we know almost everything. We can calculate the risks and everything, but it's still this stigma that radiation and nuclear has. And of course, we need to educate the public, but we also need to educate politicians, journalists. Every week I see something posted somewhere, something in a newspaper, something on internet that's completely wrong. And you can't argue with these people because they are absolutely sure that they are right. So there's a huge amount of misunderstanding that's around, and having an acceptance that this is a possible solution, we need to inform, in principle, the general public as well as everybody else to really present the facts.
Thank you. We have a quick follow-up before moving to the other questions.
It is a quick follow-up. I mean, I can see you started. I mean, we realized that you'd started education at university. So if you think that the public is outside the university, and you also think that there is no such thing as a general public, we're all different. There are women, there are young people, there are old people, there are different sexes, cultures, this kind of thing. But my question is really, where should we start? With whom should we start if we're going to work with more knowledge out in wider society?
Oh, critical thinking and understanding the scientific method. If you get those things into people starting with pupils in school, then you gain quite a lot. As soon as you become critical and look up sources to find out what's true, what it's not, then there's a huge win. But as of today, when YouTubers, influencers, and others have more power towards the public opinion, then we who know these things better, we stand no chance. I'm so old, I remember the Swedish nuclear power referendum, when one person said, from one of the alternatives, said that experts should be quiet because they knew what this was all about. And I feel a bit like that nowadays as well, because I know a lot about radiation and nuclear physics. I am supposed to be quiet because somebody else who read something somewhere is more of an expert on this than I am.
Okay, interesting.
Well, I mean, all discussions should be based on knowledge and competence, and I think regarding education, I mean, this is one of the purposes of this workshop series is that we are going to educate ourselves. I mean, in process industry, it's very sort of multidisciplinary, but as Tom hinted to in his presentation, building a nuclear power plant is even more multidisciplinary. There are other aspects that comes into play that you normally don't need to consider in industry. So we're going to educate ourselves, we're going to educate students, masters and PhDs, and we are going to try to educate also the audience and politicians. As Jonas said, radiation, you can't see it. It's similar to CO, you can't see it, but it's really dangerous. So Andreas By at IFE, he said a few wise things, I believe. He said that you can measure radiation. And he also said that when you fly, take a plane to, well, I don't fly to US any longer, but if you go to Asia, you are subject to radiation. Some of the houses we have in Norway, you have radon. Not sure if that's the proper English word, under the houses. That's dangerous. And Andreas concluded by saying it's the difference between drinking 1 glass of red wine and pouring in 2 liters of moonshine. So we have to be balanced here, and we need to make sure that, I mean, in carbon capture, nobody wanted to store CO2 in their backyard. So it's the same concept here. In Halden, where they have had research reactors for many years, the people, the opinion there, the public there, are more positive towards nuclear power than other parts of Norway. So education is very important.
Okay. Next question.
Yes, in Norway the debate is often simplified to we need to build offshore wind or nuclear power. And then one of the arguments that the proponents of offshore wind use is the oil workers can easily transition to offshore wind. Do you have a comment with regards to how an oil worker can work with nuclear? Because like the last 2 or 3 slides that you had, they could be taken from a lecture that I attended to Truls 20 years ago when I was a student here. And I've been working in the oil industry ever since, you know, so yeah.
Let me address that one. I think, yeah, and I teach his course now, so you would have been with me, I think. Yeah, so just to summarize the question is the juxtaposition of nuclear versus offshore wind is like one of the decisions that Norwegians have to make in terms of where the power is going to come from. So I think it is definitely an open question. When I came here almost 4 years ago now, my main projects that I was asked to be on were hydrogen and offshore wind and those kinds of systems and things like that. The offshore wind has got some extra challenges to onshore wind in the fact that you have very, very large amounts of cabling. and because you need to put them far away, basically, from the sources where you use that power. That cabling, like if it's copper is a really actually quite energy intensive and environmentally unfriendly material to manufacture with the refining and that kind of thing, and a lot of those metals in general. And what ends up happening is the sort of, because I said I deal with life cycle impact, for example. So if you do a life cycle assessment, a lot of those studies will show that that cabling can really drastically offset the benefits you get compared to a fossil-based source. So like switching from fossil to wind can be drastically offset on the life cycle from the secondary impacts earlier in that life cycle. Another problem is that, again, you lose energy the farther away you get, because you lose energy every kilometer of transmission, and the farther you're away from shore, the less efficient those same turbines are going to be. So there's like a double penalty. I will say, I can't say with definitive, but with all the companies I've been working with and all the different research programs, the movement is away from offshore wind right now in practice, in terms of where people are looking to go next. It's a feeling I have based on conversations on that sense. I don't have, on my big greenhouse gas emission things, I don't have numbers, like I said, because it is so fuzzy and argued over. So unfortunately, I can't give you like a quantitative number.
Yeah, I mean, there's been a discussion in Parliament between the government and the opponent parties, in the sense that offshore wind seems to need a lot of subsidies. So it's not going to be very cheap. And the problem with offshore wind, as with onshore wind and solar, is that these are intermittent energy sources. So we need to build storage capacities. Could be batteries, could be other solutions. So it's. Just let me elaborate. My question was more related to
Impregnability, I think, right?
Like it's often said that we should. My question was related to. It's stated that one of the advantages choosing offshore wind is that the competence of current oil workers will be useful there, and whereas if we will nuclear, we will have to buy everything from a foreign country. But, and then, like I said, these slides, they remind me of my education that made me an oil worker.
Yeah.
So,
I understand you now, yeah. Again, this is one of those conclusions of that report about the national competency building. So one of the things that I have been talking with are some of these companies who are actually interested in using nuclear offshore on an oil platform to provide energy needs there. And it doesn't even have to be power, it could be heat. You can skip the steam cycle and that stuff, you can just use the heat, for example. Things for like propulsion of their ships that are going around, right? So they are actually turning to look at that. The competency issue is real, right? But that's a part of it. The counter argument I have heard from other people to that is that, well, we didn't know how to do oil and gas before, but we learned that. So we can learn this too. So that was a very interesting argument that I heard for that. It's a real issue that I don't have a solution for, but that is absolutely a part of the discussion.
Yeah, I'm not sure we can use the workers from the oil and gas sector, but Norway is fortunate in the sense that we have learned a lot from our oil and gas sector. One is safety. And Jørn Stene, who is professor at NTNU and part of this team, he says when you go to conferences, about half of the audience are Norwegians, and about half the presentations are Norwegian. So safety, we are at the research forefront in the world on safety. Another thing that we have or can learn from the offshore industry is project management. In the offshore sector, they go against any kind of change during the project. Once a project is decided, they should avoid changes in the design because that has a large economic penalty. So these are things that we can learn when if we go for a nuclear industry in Norway.
Okay, we are running out of time, unfortunately. I know we had more questions, but maybe we can, for those who are here physically, we continue over lunch and coffee and talk a little bit more. So just to wrap it up, I wanted each of our panelists to say, because we had a goal today, which is prepare everyone for the debate around nuclear power. If you have one thing that you want people to know better and understand better, like one key message from our event today, what is the one point that you want to highlight before we finish?
I think for me, it's just getting informed. I think the number one thing, at least even for my own learning, but within students in our courses, is that when you've taken the time to learn about the technology and about the different issues, you are at least more confidently able to make a good decision in the end of the day. And that's what Norway needs to do in the next year or two. And it's just get the information as best as you can and learn it. I think that would be the single most fundamental thing that we need.
Yeah, I don't have any specific comments. I mean, when it comes to education, which is very important here, I said the same when we had the previous meeting, that we are educating engineers, and whether they go to a fertilizer plant or a metallurgical plant, or they go to a nuclear plant, engineering, a lot of the engineering is the same. Of course, there are safety issues, there are reactor issues in atomic or in nuclear power plants, but the engineers that we educate will still be valuable.
Yeah, that would be the one thing that would be education, information. That's alpha and omega in this case.
Okay. So I guess we have work to do to inform them, and that is the key takeaway from our discussion today. I hope you had a good time, everyone. Thank you for joining us today. For those online also, thank you very much. This recording will be available on our website, so it's something that hopefully can be used further to inform more people. So thank you, and join us for a cup of coffee, and let's continue talking. Thank you very much.